March 19, paper 6, variant 2. Question 1. Student is investigating the reflection of light by a plane mirror. We have a plane mirror, and he needs to investigate the reflection of the light. Student carries out an initial experiment. He draws line AB, okay, lines AB and lines CD. AB and lines CD. As shown in figure 1.1, he then draws a line EF through the point. Can I measure the angle theta? Yes, I can measure the angle theta using the protractor. I'll simply put the protractor this way, okay, and measure the angle 0, 10, 20, okay. The angle should be 23, okay. The angle should be around 23 degrees. Do not forget to include the unit. Measure the angle theta, it would be 23 degrees. If you measure it and it's 22, okay. If you measure it and it's 24, it would be okay again. Okay, but the perfect answer would be 23 degrees. Draw a normal to line AB at point N. Line AB at point N. And extend the normal to line CD. Label the point at which the normal crosses CD with the letter L. Okay, and L, I need to draw a normal at this point, okay, which would be perpendicular. Again, you are using the ruler, okay. This is my normal. Do not draw this protractor. Okay, this is the normal. The point at which it crosses CD, this point would be L. This point would be L. Quite easy. Soon places a mirror on line EF. Line EF, I have a mirror and a screen with a 2 mm slit on line CD. He arranges the screen so that the ray of light shines along line L. The ray of light shines along line LN. The ray reflected, okay, the ray reflected from the mirror passes through point P. Okay, the ray reflected passes through point P. Can you see this point P? It's from line L all the way passing through point P. State and explain whether point P shown is at a suitable distance from point N for this investigation or not. Is point P at a suitable distance from point L? Okay. Is it at a suitable distance from point, I'm sorry, from point N? Is it at a suitable distance from point N? Where's point N? It's on the left. Okay, and this is point P. Are they at a suitable distance or not? Well, we can measure. Okay, we can measure the distance from point P to point N. You can measure this distance using a rule. Okay, you'd find the distance to be quite close. Okay, the distance between point N and point P is quite close. So it's not a suitable distance. You need to increase the distance as much as possible. Okay, you need to increase the distance from N to P as much as possible. Okay, so that the line would extend. Okay, so that the line would be more accurate. Again, these 2 points are quite close. Whenever you have 2 close points in this experiment, it would be wrong. Definitely, you need the points to be as far as possible. Statement, are they at a suitable distance? No, not at a suitable distance. Okay. What should we do? We should increase the distance between them as far as possible. Okay. Hmm. To be as far as possible. Yeah. As far as possible. Hmm. Okay. Yeah. Draw a line joining N and P. Extend the line until it meets line CD. Okay. At least 5 centimeters. يعني, okay. At least 5 centimeters. You could say more than 5 centimeters, whatever, but you need to Okay, how can we determine if the distance is suitable or not? If the distance is less than 5 centimeters, that would be wrong. Or if it is exactly 5 centimeters, you need to extend the line. Okay, you need to extend the points between, sorry, to extend the distance between 2 points. You have to always increase the distance between any 2 points. Okay, it has to be more than 5 centimeters. Yeah, draw a line joining point N and P. We have points N and P. Extend the line until it meets CD. The point at which it meets CD is G. Measure the line of LG. ماشي. Okay. Hmm. N, P. Extend the line until it A and P. Of course, you're using the ruler. Okay, so we have to use the ruler. N, P, and extend the line until it reaches. Okay, it would reach somewhere here. This would be point G. Can I measure the distance LG? Can you measure this distance? Yes, I can measure this distance using the ruler. Hmm. Distance should be around, okay, the distance should be around 10 centimeters. Okay. Um, okay, the marking scheme has it as 10.2. Okay, has it as 10.2. So most probably you are correct. Why? Because there's always a slight difference. There is always a slight difference with the printing. Okay, there's always a problem with the printing of your papers. Okay, so if you have it as 10 centimeters, that is perfect for this question. We have different values for theta and A. Okay, and then you are required to plot a graph. I can plot the graph. This is quite easy. Theta and A. Use the values to plot a graph of A on the y-axis, A slash centimeters on the y-axis, and theta slash degrees on the x-axis, theta slash degrees on the x-axis. I need to scale the graph. Hmm. A 1.8, 3.6, 5.7, 8.3, 12.2. I guess it would be reasonable to start the axes, both axes from the origin. Okay, it would be let's try it out. Okay, let's try it out. If I start A from 0, okay, if you start from 0 and then 2, 4, 6, 8, 10 and 12. Ah, that's good. 10 and 12. The maximum value for A was 12.2, so we can plot 12.2, and we can plot 1.8, so this is a suitable scale. Theta, 5, 10, 15, 20, and 25. Okay, 5, 10, 15, 20, and yeah, you can start as well. You may start from 0. It's not a must. It is not a must, but you can. Okay, 5, 10, 15, 20, and 25. Let's push the theta a little to the right. Yeah, let's plot the points. Let's zoom in and start plotting the points. 1.8, 3.6, 10. Hmm. Okay, 1.8 would be 1 square, 4, 2, and 5. Okay. 3.6, okay, this is 3. It would be 3 squares above 3 with the 10. Hmm. 5.7 and 15. 5.7. Yep, this is 5, 5.2, 5.4, 5.6, 5.7. So it's a square and a half before 6. Ah, 5.7 and 15. 8.3 and 20. 8.3, this is square and a half above 8. 20. And the last point is 12.2 and 20. 12.2. Hmm. Yeah, let's zoom out. it's not actually the best graph. Okay. Points are quite, the first 4 points were really good. The last point, 25, is very off. Okay. The last point might be an anomaly. Okay. 12, 25 and 12.2. It should have been around 10. It should have been 10 مثلا, or 10.1, 10.2. So probably this point is an anomaly. Okay. And I can just draw the graph. I can draw a straight line of best fit. He does not, in this graph, he does not want a um, gradient. He does not want to actually measure the gradient. So I can just measure the points. I can draw the line of best fit, and that's it. That would be it for this experiment. Okay. Um, okay. Yeah, let's draw a best fit line. Could be something like this. Hmm. It's actually a very, very bad graph. To be very honest, it's a really, really bad graph. You have a question?
يا مستر، هو مش اللاين اوف بس المفروض يكون ان احنا نوصل يعني اكتر points possible ببعض.
That's if it was a curve. If it was a curve. Okay. This line should not be a curve. Okay. This line should not be a curve. This should be a straight line. And that's why I'm saying the last point is an anomaly. If you had the points, okay, and the points were showing a curve, for example, if you had a rate of cooling, yeah, rate of cooling is definitely a curve. Rate of cooling is always a curve. But for this example, okay, they should be a straight line. So if I draw a straight line, okay, they should have somewhat a constant slope. Some of the points would be below the line, some of the points would be above the line. Okay, no, it would not start from here. Okay, some of the points would be above, some of the points would be below. That's okay. It should be around something like this. Okay.
يعني احنا يعني straight line، انا عايز اعرف بس straight line يعني بس اللاين اوف بس فيت في الستريت لاين بنرسمه على اساس ايه؟ يعني المفروض نقسمه على اساس ايه؟
Hmm. Okay, the
يعني
line
نحاول
of
نخليه
best
ازاي؟
fit in a graph. It should be depending on, okay, the points. Yeah, some of the points should be above, some of the points might be below. It does not have to pass through all of the points at all. Doesn't have to pass through all the points at all. Okay. If you have, for example, 2 points above, you can have 2 points below. You can have only 1 point on the line. Okay. But the thing is, you cannot have all of the points below the line. Okay. You shouldn't have all of the points below or above the line at all. You have to have, let's say, 2 points above, and you have to have 2 points below. Should you extend the line until it reaches the x-axis? You could if you want to. It's not a must. He did not state that you have to do that. Okay. You have a question?
آه.
Mr. When do I know if it's going to be a straight line or a curve?
حلو. A curve usually, okay, a curve usually, if it's a curve, he will state that it's a curve. Okay. If it's a curve, he will state that it's a curve. If he doesn't state that it's a curve, and the points are very obvious that they are a curve. For example, if you had a point like this and another point like this, and the other points are somewhat like this is definitely a curve. This is definitely a curve. For example, if you had a rate of cooling, okay, if you had the rate of cooling or something, it would be a curve. Okay, most likely the curve would be in a question that is related to the rate of cooling of water. Okay, but in this question, okay, in this question, it has to do with what? It has to do with the reflection of light. It has to do with the angles. It has to do with the measurements. So these measurements should be somewhat, okay, they should be somewhat directly proportion, okay, or at least proportion. It doesn't have to be directly proportional, but they have to be at least linear. It should be a straight line. And that's why I'm saying this point is an anomaly. Okay, the last point is an anomaly. Why? Because it's very obvious. The four other points are very close. The four other points are almost on the same line. Okay, this is the only point that is very far away. That's what I'm saying. This is an anomaly because it is very far away from the other points. That's the whole point. Okay, I hope you all get this question. Okay. Um, yeah, moving on. Suggest a possible source of inaccuracy in this experiment. This is the inaccuracy. The last one was inaccurate. What was one possible source of inaccuracy for this experiment? Okay, you have some sources that could, okay, some possible sources of inaccuracy for this experiment. One of the possible sources, okay, for example, if you have a mirror, usually we say if you have a mirror, usually one of the more famous possible sources is the thickness of the mirror. Okay, the thickness of the mirror, okay, usually is a possible source of inaccuracy. Okay, sometimes you can say yes, the thickness of the lines. Okay, sometimes you can say the thickness of the lines, but for me, I would preferably say that thickness of this experiment of the mirror. Why? Because we have a mirror. If you have a mirror, it would be better to say the thickness of the thickness of the mirror. Okay. Hmm. Student wishes to check if his values for A are reliable. Okay, the values of A, are they reliable or not? So just how he could improve the experiment using the same apparatus to check the reliability of his results. Okay, how can he check if the results are reliable? Okay, how can he check if these results are correct or not? All he needs to do is what? He needs to repeat and take average. Okay. He needs to repeat and take average. For example, he would find that the last point, which is 12.2, is wrong. Okay. If he had taken an average, if he had taken an average for this specific angle, which was 25, okay, if he had repeated this experiment at the 25 degrees, he would have found that the measurement of A was wrong. So how would he obtain more reliable results? He would repeat and take average. Okay. Okay. Repeat with the same angles and take average. Okay. Hmm. Any questions? Hmm. Question 2. Record the room temperature. I can record the room temperature. It's quite easy. It is 23 degrees Celsius. 100 centimeters cubed of hot water is poured into beaker A, okay, which had insulation. Beaker B had a lid. You had the same initial amount of water, the same initial volume, and you poured it into beaker B. Beaker A had an insulation, beaker B had a lid, and now we will test the difference, okay, in heat loss between a lid and an insulation. We need to complete the headings and the time column. The time is 30, 60, 90. This is quite easy. 90, 120, 150, and 180. The time is seconds, degrees, and the temperature, theta, is degrees Celsius. Okay, yeah, three very easy marks. Right, the conclusion stating whether the insulation or the lid is more effective in reducing the cooling rate. Okay. Um, hmm. Which of them is more effective in reducing the cooling rate, not increasing the cooling rate, reducing the cooling rate? 83. What should we do? 83 minus 68.5. 83 minus 68.5. 5. This would give me a difference of 14.5. Okay, this would give me a difference of 14.5. The other one would be 86 minus 78.5. This is a difference of only 7.5 degrees Celsius. Again, correct me if I am wrong. 14.5 and 7.5, which is more effective? Which is more effective in reducing, in reducing the rate of cooling? Okay, reducing the rate of cooling would be definitely the lid, not the insulation. Why? Because the difference between the initial temperature and the final temperature is less. If you have a less difference, okay, between the initial temperature and the final temperature, this means that it is more effective. This means that it has a reduced, okay, it has what a reduced rate of cooling. So definitely, which is more effective, the lid, okay, the lid is more effective. Why is it more effective? Because the difference, hmm, beaker B, beaker B had a difference, had a temperature difference of 7.5 degrees Celsius. Beaker A had a temperature difference of 14.5 degrees Celsius. Okay, it's quite obvious. It is quite obvious for this question. Another student thinks that the experiment does not show how effective the insulation is on its own or how effective the lid is on its own. Suggest an additional experiment which could be used to show how effective a lid or an insulation is. This is a really good question. This is actually a really important question for any experiment, literally for any experiment. Now, I do not know if the lid is actually effective or not, or if the insulation is actually effective or not. If there is any effect or not on the whole experiment, how can I test? Okay, how can I test if they are actually effective or not? I need a control experiment. Okay, you need a control. What do I mean by control experiment? You need an experiment without a lid and without an insulation. That's the thing. Okay, that is the whole question. You actually need an experiment without a lid and without an insulation. Why? Because you need to measure the initial rate of cooling without anything, and then, okay, and then you would see, for example, if you have the control experiment, which is without any lid, without any uh, insulation, probably the rate of cooling would have been, or the difference in temperature would have been much more than 14.5. It would have been 18, 19, 20. Okay. So now when you find that the rate of cooling are 14.5 and the other one is 7.5, there is a significant difference. Yes, the insulation has uh, decreased the rate of cooling, and the lid has also decreased the rate of cooling. Okay, so as for the additional experiment, okay, you need to repeat, okay, the experiment with no lid and or insulation. Repeat the experiment with no lid or insulation. You have to repeat it with no lid or insulation. Why? Because you need to test, okay? You need to compare whether the results are, whether there is whether there's a difference or not, okay? You need to compare, okay, whether there's a difference or not. That's it. Okay. It's a really, really important question, actually, to be honest. It's a really important question. Hmm. Okay, yeah, moving on. Can I find the rate of cooling for beaker A over the whole 180 seconds? Yes, I can do that. Theta 0 minus theta 80 over 184. Theta A, 83 minus 68.5, which is 14.5, divided by 180, divided by the time. Theta 0, 83 minus, what we said 60, 68.5? I forgot the numbers. 68.5, yes. Yeah, 68.5 divided by 180. This would give me a rate of cooling of 0.081. 0.081. Include the unit. Degrees Celsius, and the time is in seconds. So degrees Celsius per seconds. Students in another school are carrying out this experiment using the identical equipment. State why they should make the initial temperature of the water the same as in this experiment if they are to obtain average cooling rates that are the same as in table 2.1. Assume that the room temperature is the same. Okay, assume that the room temperature is not changed. Use the results from beaker A to explain why this factor should be controlled. Statement. Should they use, okay, why should they use the same initial temperature? Okay, it is a must for them to use the same initial temperature, but the question is, why should they use the same initial temperatures? We can check the values we have in the table. Okay, you can check the values you have in the table. As the temperature decreases, okay, as the temperature decreases, what happens to the rate of cooling? The rate of cooling also decreases. Or, in other words, if you have a higher initial temperature, okay, if you have a higher initial temperature, then you will have a much higher rate of cooling. That's it. Okay, that's it. And that's something you have to know. That's something you must know for any question that is related to the rate of cooling. As the temperature increases, as the difference between the initial temperature and the room temperature, for example, as the difference increases, what happens? The rate of cooling also increases. Yeah, use statements from the beaker A to explain why this factor should be controlled. Statement, as the initial temperature increases, okay, okay, as the initial temperature increases, okay, increases the rate of cooling. Okay, the rate of cooling increases. Again, we need to use results from beaker A. How can I use the results from beaker A? For example, if I test the results for the first, let's say, 90 seconds, okay, for the first 90 seconds, the difference is 10 degrees. For the second 90 seconds, difference is only 4.5 degrees. Okay. In the first in the first 90 seconds, okay, beaker A in the first 90 seconds, the temperature difference was 10 degrees Celsius. The second 90 seconds, the temperature difference was only 4.5 degrees Celsius. That's it. Okay. That's the whole point. The initial temperature, okay? The initial temperature, shabab, was, for example, in beaker A, in the first 90 seconds, the initial temperature was 83. Okay, it dropped all the way to 73. The initial temperature in the second 90 degrees was, in the second 90 seconds was 73. It dropped only to 68.5, so it only dropped 4.5 degrees. Would it differ if we use the second before the Celsius in the unit? In the unit يا شباب, if you لا لا in the unit it would differ. Yes, it would differ. You have to, in the unit of the rate of cooling, you must write it down as degrees Celsius per second. Okay, you must write it down as degrees Celsius per second. Again, for this question, okay, as the temperature drops, as the temperature is approaching the room temperature, as the temperature difference is getting smaller, as the temperature is getting closer to the room temperature, whenever the temperature decreases, the rate of cooling decreases. And that's the case for beaker A. In the first 90 seconds, it dropped 10 degrees. But in the second 90 seconds, it only dropped 4.5 degrees. And that's the whole point. As the temperature decreases even more. For example, if you left it for 90 more seconds, what would have happened? The temperature difference would have been less than 4.5. It would have been, for example, only 3 or 2.5 degrees Celsius. Okay? Yeah. Question 3. Yeah, very quickly. We have a um, circuit. On figure 3.1, draw a voltmeter to measure the potential difference between P and Q. Yeah, this is a very easy voltmeter between P and Q. The student connects the crocodile clip, okay, at a length of 90 centimeters. Okay, the crocodile clip has a length of 90 centimeters. Can I take the measurement of V and A? Can I take the measurement of the voltage and the current and record them in the table? Yes, I can do that. The voltage is 2.6 and the current is 0.36. Yeah, 36 and the other one is 2.6. 2.6 and 0.36. Can I fill up the column headings? Yes. The voltage in V and the current in amperes. Calculate the resistance. Can I calculate each of these resistances? Yes. R equals V over I for each of the lengths. I can calculate it. Okay. The first one is 2.6 divided by 0.36 is 7.2. Okay, you can write it down as 7.2 or 7.22. 2.5 divided by 0.52. Okay. 4.8. Last one, 2.3 divided by 0.71 is 3.2. Now, can I calculate and record R over L for each length? Yes, I can calculate R over L. 7.2 divided by 90. 4.8 divided by 60. That would be easy. 7.8 divided by 90 is 0.087. 0.087. 4.8 divided by 60. 0.080. The last one is 3.2 divided by 40. This is 0.080 as well. Can I calculate the resistance? Can I calculate the resistance if the length was 25 centimeters? Can I calculate the resistance if the length was 25 centimeters? Yes, I can do that. How can I do that? How can I do that? Cross multiplication. Cross multiplication. It is directly proportional. What do I mean? For example, I'll take the readings of the 40 and 3.2. 40, when the length was 40, the resistance was 3.2. What if the length becomes 25? Can I calculate the resistance? Yes, I can cross multiply it. 25 times 3.2 divided by 40 would give me a total resistance of 2.0. Okay, 2.0 ohms. Cross multiplication 25 times 3.2 divided by 40. Okay, this is easy. Suggest one reason why different students carrying out the same experiment with same equipment may not obtain identical results. Why might not all of these students obtain the similar or the same results? It's a very logical reason. Okay, it is a very logical reason. Why might they not all have the same results? Um, some of them, for example, might not use the same length. Okay, some of them might have not taken the readings quite accurately. Okay. Um, for example, some of them not taking the readings accurately. How would they not take the readings accurately? They wouldn't have been able to measure the readings on the wire very accurately because there was a problem with the crocodile clips or whatever. Okay. So for example, okay, one of the logical reasons is, okay, they didn't take the readings accurately, the readings of the crocodile clips, okay, or the, sorry, the readings of the length between the crocodile clips accurately, of the length between the crocodile accurately. Okay. Hmm. Yeah, we're almost done. Um, the student finds that during the experiment, the wire becomes hot because of high current. She decides to use a variable resistor to prevent this. Complete the circuit to show a variable resistor used for this purpose in the experiment. Okay, we had the resistance wire. Okay, let's check out the initial drawing. We had an ammeter, okay? We had the resistance wire, we had the voltmeter. Can we draw a can we draw a variable resistor? Yes, we can draw the variable resistor. This variable resistor would be instead of the crocodile clip, okay? It would be instead of the crocodile clip. Why? Because it will change the current, okay? Um, it doesn't have actually to be instead of the crocodile clip. It could be with the crocodile clip. How can we draw the variable resistor? It would be in series. Okay, this is the variable resistor. We have the ammeter. Okay, if you want to draw, for example, the crocodile clip, and then we can just draw the same voltmeter. But the thing is, the whole point is that the variable resistor has to be in series. Why does the variable resistor have to be in series? Because it will control the whole current of the circuit. Okay, it will definitely control the whole current of the circuit. Okay, يلا, moving on. Plan and experiment. Okay, planning and experiment. How can I plan this experiment? The student what does the student want to do? He wants to investigate the effect of air resistance on the swing of a pendulum. Okay, he wants to investigate the air resistance. Plan an experiment which will enable him to investigate how air resistance changes the way which a pendulum swings. How can air resistance plan experiment which will enable him to what? To investigate how air resistance changes the way in which a pendulum swings. This is actually it's a rather different, rather new experiment. The whole point is, how will you change the air resistance on a pendulum? That's the question. That's actually the main problem with this question. Other than that, the question would be quite easy. We know how to find the period of a pendulum, okay, in which the pendulum, in which Okay, we can find the period of the pendulum, we can find the mass, we can find the length, we can do everything we want with a pendulum, but how can I change the air resistance of a pendulum? The apparatuses available are what? A light wooden rod, okay, approximately 80 centimeters long with a hole at one end through which a nail will be fit. Okay, this is the rod at which we have the nail, okay, and the pendulum will start to swing from this rod. A piece of modern clay that will act as the pendulum bob, okay. A sheet of thick cord which will provide the air resistance when the pendulum swings, okay. You have a sheet of thick cord, and that's how you will change the air resistance. Okay, this is how will I change the air resistance using this thick cord? Yes, using the thick cord. Okay, you have the nail as drawn. Okay, you have the nail, you have the pendulum. Okay, the pendulum uh will start to oscillate from left to right. Okay, what will you do with this thick card? What will I do with this piece of card? I'll just attach the piece of card to the pendulum. Okay. I will attach the piece of card to the pendulum. But the thing is, I will increase the area of this card. Okay. For example, I have a small piece of card, a larger piece of, okay. I'll just increase the area of this card. And whenever I increase the area, the surface area of the card, what happens to the air resistance? The air resistance also increases. So whenever you increase the air resistance, what happens to the period of the pendulum? I will test what will happen to the period of the pendulum. Okay, that's the whole point. That's how we will change the um, the air resistance of this pendulum. Okay, for example, I will attach the piece of card this way. Okay. Um, just anyway, okay, any way possible, any direction you want, okay? You can just attach the piece of card to the pendulum and you keep on changing the area of this piece of card and you keep on repeating the experiment. And for each experiment, you will measure the period. Of course, you are required to list any additional apparatuses. Definitely, the missing apparatus for this question is the stopwatch, okay? Is the stopwatch and a ruler, for example. Okay, you need a ruler. Why do I need a ruler? I need a ruler to measure the length of the pendulum. I need the ruler to measure the area, okay, of this piece of cord. So now, let's start off with the range of values, okay? The range of values. What are the range of values? The area of the piece of cord, okay? The area of the card. Let's say, for example, 10 centimeters squared, 20 centimeters squared, okay, 30, 40, and definitely 50 centimeters squared. So these are the different values for the area of the card, okay? Next point, what are the controlled variables, okay? Controlled variables. The controlled variables would be the mass of the bob, the length of the wooden rod, okay, the length of the rod, okay, um, let's say the number of swings, maybe. But more importantly, actually, more importantly than the number of swings, you need to have the same angle, okay, same angle, okay, 30 degrees, 20 degrees, 25 degrees, okay. Um, okay, these are some of the controlled variables. And then we need to state the apparatuses used. We have three main apparatuses. This is a pendulum. We know the three apparatuses. What are the three apparatuses? The okay, you need a ruler, you need a ruler, you need a protractor, and you might need a balance. Okay. What about okay, we wrote down the key variables. We need to write down the method and then a table. What is the method? What are the steps we will do? Okay, for each area of cards. Let the pendulum swing. Let's say for 20 oscillations. Okay, let the pendulum swing for 20 oscillations. Measure the time taken. Measure the time taken. Okay, after you measure the time taken, divide. Okay, divide the time by 20 to find the average period. The average period of the pendulum. That's it. Okay. And then you must repeat for all the different areas of the card. You have to say that. Repeat the experiment for all areas of the cards. That's it. That's the method. That is the method you are required to write down. What about the table? What should we write down in the table? The table. The area in centimeters squared. The time taken. Okay. The card will be from one side. Yes, from only one side. Area. The time taken in seconds. And then the period in also seconds. The period in seconds. If you want to write down, for example, the length of the pendulum, the mass of the bob, whatever, it's okay. But these are the main 3 points, the main three columns you need in this table. Okay. Resistance. You're not measuring resistance. You are not measuring the resistance. You are experimenting whether the air resistance would affect the period or not. For example, you have the initial area, which was 10 centimeters squared. You'll find out the period. And then 20, 30, 40, 50. Okay. By the time you reach 50, the period should increase. Okay. You're not required to write that down. But for example, whenever the area or the air resistance increases, the the period of the pendulum would also increase. Why? Because it's taking more time to complete one full oscillation. Okay. The conclusion. Yeah. For the conclusion, we have to say for each area, repeat and take for each area, repeat and take average. Repeat and take average. After you repeat and take average, what should you do? Record the readings. Record the readings in the table. After you record the readings in the table, you have to compare the results, whether, okay, the area of the card, okay, the area of the card affects the period or not. Okay, that's it. That's it.